molecules. The first thing is, of course, what you just did. Okay, is just writing out the structures. And did you try out the sulfate and the phosphate? Mm-hmm. Yes? Okay. Yes?
Yes.
I hear here. Anyone from there? Okay, well, keep up, all right? Please don't let it go, because you will forget to do it, and then you will forget how to do it. So don't forget, okay? Please keep doing it. One of the things that does happen, okay, with structures is that sometimes I may give you the same molecule, I may give you one molecule, but two of you may have different structures, okay, for it slightly, and then you might wonder which one is correct, okay? And that can happen, all right? It does happen, especially with polyatomic ions. Even with some other structures it can happen, okay? That you can have a different structure from your friend or from anyone, okay? Or you may yourself, okay, be creative enough to write more than one structure, okay? So let me give you an example. We worked on carbonate ion last time, correct? And you have the structure with you. And I don't know if all of you, can I just see yours, Dylan, for a second? Okay, what you have. I think that's what I drew out too, okay, on the board. Oxygen, oxygen, and then here we have all the lone pairs. And that's what we wrote. Is that what you all have? Mm-hmm. Yes? Very good in copying. Okay, fantastic. So, what happens if I change this a little bit? So, for example, if I do this, is this the same structure?
Yes.
What if I do this? And you're most welcome to go ahead and copy this as well. Yes? They all look the same to you? Yes? Okay. And you can see what the difference is also, right? Despite the fact that you think they're the same, you can see the difference. I've moved the double bond, right, around. And actually, this is an actual process that happens in the molecule, all right? Because if I had given you the structure to write on your own, maybe some of you would have written your double bond over here. Maybe some of you would have written it on this oxygen. Who knows? Okay, so you can have a variety of structures that way. And you're right, okay? They all look exactly the same. And this process over here where you can have more than one structure, okay, like this, where you're just moving a double bond around, this is called resonance. And in resonance, you have more than one kind of structure, okay, in here. Now here we're dealing only with one carbon and one oxygen. Did I move any of those, by the way? Did I change the framework of the polyatomic ion? No, my carbon is still in the middle, right? I didn't change the oxygen in the middle, so I did not do anything like this. It would be totally illegal for me to do that anyway, okay, because oxygen right now cannot have 3 bonds as far as we know. So I didn't do this, okay? As soon as you do this, you have a completely different structure, and that is not counted as a resonance structure, okay? So in a resonance structure, you can have different kinds of structures, but with the same framework, but the electrons are moving around, okay? All right, so let me ask you to go ahead and write me a structure for ozone. Go ahead, try it out. Ozone is 3 oxygens, so see if you can write the Lewis structure for it, and be creative as much as possible. I really don't mind. Be creative, and I will give you a clue. Oxygen can have 3 bonds. Okay, it's all right. Ozone. A lot of you writing the structure, okay? And so oxygen here with double bond can have, sorry,
2.
2. Okay, 2 lone pair of electrons. And then oxygen with a single bond can have up to 3 there, okay? How many electrons right now on this oxygen?
6.
6. Okay, 1, 2, 3, 4, 5, 6 electrons, okay? And oxygen itself has 6 electrons, correct? Okay, so how many of these electrons belong to oxygen right now? How many of these electrons belong to the oxygen?
3.
3, okay, because 1 is bonded, right? And there are 3 valence electrons, so how many electrons remaining for me to assign? 3 electrons remaining to assign, okay, for it. So it's a weird looking structure, okay, and some of you may actually have this, right? The double bond on the other side, and then somebody who's even more creative has something like this, a cyclic structure, which we really haven't ventured into cyclic structures, okay, at all. And this is what happens, okay, when you have resonance, is you start having all of these issues, okay, is where do I draw my double bond? How do I draw the structure? Okay, so sometimes it's a little bit of an issue, but the best thing to do when you start having these kind of things is just make sure that you're following your octet rule. Okay, that's it. That's one of the main things that you have to follow through is follow the octet rule. Make sure you don't have excess or less electrons, okay, in there. Today we're going to go into something which will help you a little bit, okay, in deciding as to whether the structure is possible or not, whether the structure is possible or not. Is this stable? Is this the most stable structure? What is it? Okay, and that is called formal charge. But otherwise, it's sometimes a little harder to decide, you know, which resonance structure is actually the structure. These 3 structures that you have here for carbonate, these are all valid structures, okay, of carbonate. And when we say that we have resonance, essentially we write this kind of an arrow between them. It's a very specific arrow, okay, the 2-headed arrow going on both sides. And what that means is that electrons are actually moving around. So here, and I'll just write one arrow all the way. So here you move this, and this goes over here. Okay, what happened?
I know what you're for.
Oh, thank you. Yeah, I would roll over that. Okay. So move the electrons here, but that's really what the movement is going on. Okay, is you're moving a lone pair of electrons over here to form the double bond, and then the lone pair here moves to this oxygen over here. So when you have these kind of movements of electrons going on, that's what gives you resonance structures. Okay, and so this is a very common thing, and generally what ends up happening, and then here, let me write you one more. So there and that. Okay, if you're interested. So that's how the electron pair moves. And so essentially what happens is that because of this movement of electrons that's going on everywhere, you tend to have something like this. A semi-double bond, single bond over all of it. And so when you write the 2-, you really cannot tell where exactly that charge is, okay, because it's spread all over. And that's about it that I'm going to do for resonance. Okay, it's not a whole lot. There is an assignment out there for you if you want to look over it. Okay, there is some resonance problems in there. So go through that if you want to, and if you're not able to do it, don't panic, okay, that you can't do it. But at least try it out, okay? So there are a few rules for resonance. Number 1, okay, you can only move electrons around. If you move atoms, you have a whole different structure then, okay? It's not the same thing anymore. And the second rule, most important rule, follow the octet. Okay, that's it. So you can't violate any rules. Everything still has to be followed, okay? That's about it that I'll do for resonance. And then let's get into formal charge. When we talk about formal charge, I always think of a tuxedo, but it's not that formal. It's actually quite informal. But a formal charge is when you start assigning the charge on each of the atoms. Okay, so for example, as I said to you over here, all of this structure here has a charge of -2. But where does that negative actually belong? Okay, does it belong to the carbon? Does it belong to the oxygen? So that's the calculation we have to do for formal charge, okay, to figure out exactly where that negative charge is. When we write hydroxide ion, we just write hydroxide. But does that negative belong to H or does it belong to oxygen? Okay, so that we don't know. And that's what the formal charge calculation is for, okay, is to figure this out. So we'll go ahead and take a small molecule, okay, and then start from there, and I can start from hydroxide itself. And here's what we have. You have to have the correct Lewis structure, okay, for everything that we're doing now and everything that we will do in the next chapter. Okay, you have to have the correct Lewis structure. So if that's not there, you're missing out a lot. Is this correct? Or am I missing something?
Missing a lone electron.
On what?
Oxygen.
Very good. Okay, so I have to write the lone pair of electrons on oxygen. Okay, without that, my Lewis structure is not complete. And because this is a single bond oxygen, I should go ahead and put how many lone pairs? 3 lone pairs of electrons. Very good. Okay. Otherwise, you know how to do the electronic bookkeeping, right? Count the total number of electrons you have on hydrogen, on oxygen, add the charge, and that's your total number of electrons. Okay. So really quickly, oxygen has 6 plus 1 plus 1, and that is equal to a total of 8. Okay. And 1, 2, 3, 4. So we have total of 8 electrons. Okay. So we're all very good, okay, as far as that's concerned. Okay, now for calculating the formal charge, okay, for all of this, you can calculate the formal charge for oxygen as well as hydrogen, okay, in order to figure out where exactly the negative belongs, okay, does it belong on oxygen or hydrogen. So to do this, there is a little bit of a formula, okay, and the formula in the textbook is a little bit different than what I use, okay, and I think it's given to you on this also. Where is my little, what do you call, summary, chapter summary as well. So that's there as well. So formal charge, which FC, okay, if you want to abbreviate that. So formal charge is the number of valence electrons minus lone pair electrons and this is where I differ from the textbook sometimes because I want to make my life easy and not hard. The less math I have to do sometimes, the better it is, especially now. I'm just done with the math. Over here, the book says technically that you're supposed to take all the bonds that you have and divide it by half. I just count the number of bonds. That's it. Okay. What you need is the number of electrons. Okay, in there. So what I do is number of bonds. What does the number of bonds tell you? It tells you how many electrons that particular atom has. Okay, that's what it's telling you. So really, what you're doing is you're counting all the electrons. Valence electrons is what is supposed to be from the periodic table. Okay, that's what you find out from the group number. Lone pair of electrons, it is what is left over. And then the number of bonds is how many bonding electrons you have. Okay, so you're counted for all the electrons there. Are we good so far? Okay, so what the textbook does, okay, it takes half of the bonding electrons. And half of the bonding electrons will be the number of bonds. Do you see that? Yes? Okay, hopefully you do. All right, okay, so let's do this. And then you add everything up, okay, all of this up, and that's how you get your formal charge. Okay, so that's what we're going to do for oxygen as well as hydrogen. All right, let's take a simple one. Let's take hydrogen because it has only 1 electron. Okay, so we'll take that first. So hydrogen, okay, and I'll take it systematically. Valence electron is 1. And that's why we use the shorthand, so you know exactly what kind of electrons you're dealing with, okay? So try to write that as much as possible, so when you go home, you know what it means. Did you write everything out here also? Explanation? Okay, good. All right, if not, it's here also in your chapter summary. Okay, so 1 valence electron, how many lone pairs on a hydrogen? 0, right? None. So minus 0 for lone pair, and how many number of bonds does it have?
1.
1. Okay, 1 bond, so you subtract that. And so 1 minus 1, or minus 0, is big fat 0. which means hydrogen does not have any charge right now, which is perfect. Then it must be that oxygen has the charge, but we'll calculate that too. Okay, so then for oxygen, how many valence electrons? Periodic table? 6. 6 valence electrons. How many lone pair of electrons? 6, right? Not lone pairs as in pairs. How many lone pairs of electrons as in number of electrons? Okay, so that is 6. Good. And how many bonds? 1 bond. So minus 1. So 6 minus 6 minus 1 is minus 1. Which means that oxygen has the formal charge of minus 1. Are we good? Yes.
Wouldn't we have already known that since hydrogen is positive 1 and oxygen is negative 2?
It doesn't work that way. Yeah, probably it will work for you here because this is simple. But sometimes when it gets more complicated like this, then it may not be so easy to do. Okay, yeah. Because when you have many atoms, then you have to calculate for each atom. All right, and there, yeah. So, but you're right, actually it worked out for this one. Okay, very easily, but yeah, not for all. Okay, that's the basic calculation. Let me go ahead and take carbonate also. Okay, and let's do that really quick. The different kinds of atoms we have on carbonate. Well, so here, so not the oxygen with the negative. Have double bond, oxygen here, and that. So I have carbon, that is a separate atom. These two oxygens are different, right? The double bonded oxygen and a single bonded oxygen. Okay, those two are different. So I'm going to have to calculate for these three. These two oxygens technically should be the same. Okay, so calculating the formal charge, can we do this fast now? What do you think? Yeah? Okay, let's try this. So carbon here, how many valence electrons? Participation. 4, right? 4 valence electrons. Does it have any lone pair electrons? No.
No.
And bonding electrons?
4.
4. 4 number of bonds. That gives you 0. Good?
Yep.
Okay. For the next one, I would like all of you to talk with me if you could. Okay, now show me that you're with me. Okay, good. I'm going to do for this oxygen over here. So how many valence electrons?
6.
All right. Lone pairs?
2.
4. Total, not pairs. Lone pair electrons as in total number of electrons, okay? Not the pair as in 2 pairs, although I understand you. Okay, but make sure you count the total electrons. Don't pair them up. Okay, and the number of bonds?
2.
2. Okay, so subtract. And then 0. Okay, do that for that oxygen. I'll wait for you. Okay, valence electrons.
6.
All right, lone pairs total.
6.
Bonds.
1.
Hold on. Lone pairs. 1, 2, 3 times 2, 6. 1 bond over here. So that's a negative 1. Okay, so that oxygen actually has negative 1 charge on it. This oxygen on the left-hand side is also the same as this one, so that should also have the negative 1. So when we write the carbonate ion out, okay, what that means is neither the carbon has the negative on it, and nor does one of the oxygen. 2 of the oxygens actually have the negative charge on it, okay? Why is this important, you think? This is important for organic a lot more, okay? And then the other part of calculating formal charge is to figure out whether the structure is right or not, okay? So one thing is the resonance, okay, that helps you figure out whether your structure is good or not. because if the resonance doesn't quite work out, then it's probably not the right structure, okay? And then the other part is the formal charge. For the formal charge, the rule is the less number of charges you have on a structure, the more stable it is. So the more neutral it is, the more stable it is going to be. Okay, that's the whole philosophy about formal charges, which is why we calculate them. So if I give you two structures, okay, of the same compound, and I ask you which one do you think is better, and if you think that everything looks fine, the octet rule is fine, the structure is similar in skeleton and everything, then the only thing you have to compare between the two is the formal charges. Okay, and if one has more formal charges than the other, then the neutral one is correct one. Okay, that's the more probable structure. Are we good? Yes? Okay. Sulfuric acid. H2SO4. If I have to write the Lewis structure of this, which I have to right now, I just can't live without it right now, what is my central atom going to be? I think I mentioned to you about that if you have to decide between left and right, it will be left. From top to down, it's going to be down. Okay? So if you're deciding between these two, it should be the whatever is down below. That should be in the center. So what's going to be in the center? Sulfur then. Okay, that's going to be in the center. So go ahead and write a Lewis structure for that, whatever you feel like. Just remember it has to be compact. Okay, it has to be a compact structure. Sulfur also has expanded valence shell. Don't forget that because it's in the third group, or third row. Okay, so it can have expanded shell. I'll give you one hint, okay, for this. The hydrogens have to be attached to oxygen. It's an acid, so when you're writing Lewis structure for acids, the hydrogens have to be attached to oxygen. So it's not as compact as we think it is. Good? Okay. So I'm going to write one structure over here, and I'm going to make sure that I have all my electrons in place. So I should have 32 electrons, and right now I have 1, 2, 3, 4, 5, 6. 6 times 2, 12. So that leaves me with 20 electrons. Okay, and then there. We do that minus 8, and that gives me 12. Good? Is that a valid structure? Did I lose any electrons? No? Okay. And then I saw that some of you have this structure. It should also have 32 electrons, correct? Okay, so let's go ahead and fill the electrons out. How many do we have right now? We have 1, 2, 3, 4, 5, 6, 7, 8. So that's 16 electrons, so 32 minus 16, that is 6, and then 1. 16 electrons remaining, and oxygen has 2 bonds everywhere, right? So if it has 2 bonds everywhere, then they all look the same. Does that make sense to everybody? Okay. If it was one single or one 3-bond thing, you know, that would be different, all right? But it all has 2 bonds, so which means all the oxygens are equal, so I can divide this by 4, all right? 16 divided by 4? 4. 1, 2, 1, 2, 1, 2, 1, 2. Good? Electronically happy? Okay. Electronically, both structures are fine. Now we're going to use our beautiful knowledge that we just learned about formal charges and then figure out which is the actual structure. Okay, for this. Is it the left one or is it the right one? Okay, and so let's go ahead and calculate formal charges for this oxygen, and sulfur, because the ones with the OHs are the same, the oxygens with the singles are the same, and sulfur here is just sulfur. Okay, so go ahead, don't wait for me, okay? And then here also we're going to do the same thing. We're going to calculate for this oxygen, and sulfur. Is that what you have for the first one? Yes? Good. Okay. And then here quickly, 6 valence electrons, and then 4 lone pairs, and then 2 bonds, minus, minus, that's 0 over there. Sulfur here, 6 valence electrons, and no lone pairs, and then 6 bonds, minus, minus, that's 0. And then oxygen here, 6 valence electrons, 4, great 10, 4 lone pairs, and 2 bonds, 0. Are we good? Do you have any questions regarding any of the calculations, first of all? Okay, all right. So looking at the two calculations that we've done for the first structure and the second one, which one do you think is highly likely? The second one, because it has less formal charges. Everything is 0, 0, 0, okay, everywhere. So that is more likely to be the structure of sulfuric acid and not this one, okay, because here sulfur has +2, and then you have 2 oxygens each with -1. So electronically everything is happy, but formal charge-wise it's not happy, okay? So that's why the first structure is not possible, the second one is possible, okay? That's how you use formal charges to figure out if you have the correct structure or not. Okay, you're gonna have to calculate this also for me, okay? Formal charges, and this is the only way you do it, okay? You have to have your right Lewis structure though. If you don't have the correct Lewis structure, then you will miss out on the electrons, okay? So keep practicing the Lewis structures. Again, on that worksheet, okay, that I did not print out, but it's up there on the web, you have practice on that as well. Okay, and the next thing to talk about, still in this chapter, is polar bonds. Polar covalent bonds. When we started talking about bonding and all that, I mentioned the 2 bonds, ionic and covalent. Ionic is transfer, covalent is sharing. Okay, and I mentioned to you back then that sharing has issues. Okay, and usually when we think about sharing, initially when we started writing the structure, we said, okay, it's supposed to be equal sharing of electrons. Okay, but that doesn't happen in some cases. Okay, you don't get equal sharing of electrons. So which means that in some cases you have an unequal sharing of electrons, which means that one atom is more greedy, okay, than the other one. It wants more electrons. So how is it that you decide which one is more greedy, which one is going to have more electrons? And that is based on what is called electronegativity. And electronegativity is a property of an atom, but not by itself as such, but only in a bond. Okay, electronegativity is the pull or attraction of electrons in a covalent bond. And this is the key part here, okay, the bonding part. It has to be in a bond, so it's not just by itself. Okay, so fine, great. You know, some atoms like more electrons and they put electrons towards themselves. So how do you know which one is which in the periodic table? The trend is it increases this way and decreases as you go down the periodic table. That's the trend. In case you're wondering, are you wondering? I don't know why this happens. Are you wondering why this happens? No? Okay, well then don't worry about it. So, but anyhow, electronegativity increases as you go to the right, decreases as you go down, and please remember the noble gases are not part of bonding, so the noble gas column is not involved here. Okay, so we're not talking about group 8, we go up to group 7, okay, for this one. So technically speaking, what is the highest electronegative element on the periodic table?
Fluorine.
Fluorine. Okay, fluorine is the highest electronegative element on the periodic table. And this causes issues. Okay, and you will see that as we keep learning more and more about molecules and the properties of molecules, this really causes different properties in certain molecules because of that. Okay, property. So it's a very key property, and it will keep coming up. It will come up now. It will come up in the next chapter. It will come up in next semester for 1046 if you're in there, and it will come up in organic 1 and 2 if you're in there. It'll come in biochem. It'll come everywhere. Okay, so electronegativity is one of those concepts, okay, that's very, very integral to all molecules. Okay, so how does this work? Let's say you have hydrogen, H and H, okay? Now hydrogen is the same atom, so which means that when the electrons are being shared, they're being shared equally, okay, very nicely, no problem. The same thing would be true if you had chlorine. Again, chlorine is the same atom. These are called homotopic, the same atom. All right, and so if they're the same thing, then really there's no difference, okay, in electronegativity. It's a nice sharing going on, okay, for electrons. But as soon as I have hydrogen and chlorine, now we start having issues because now we have different atoms attached here. So then, which one is more electronegative? That's what you have to figure out. So you look at the periodic table and it is chlorine, okay, that's more electronegative, which means that chlorine is going to pull electrons towards itself. The way we indicate that in a bond is by a small arrow that shows that electrons are being pulled towards chlorine, okay. What does this mean for us? It means that there is no equal distribution, okay, of electrons. If it is not an equal distribution, here is what it's supposed to look like, okay, is when you have an electron being shared, that is what it's supposed to be. Okay, remember electrons are like clouds, okay, that are being shared. So if you have this cloud of electrons that's being shared, this is what it should be, but this is not what happens because chlorine is more electronegative, and because it's more electronegative, the cloud suddenly takes a little bit more shape and it's a little bit more like a teardrop instead of a nice oval, and I can't draw a teardrop. There, is that better? So you have a higher density of electrons towards chlorine. Because you have a little bit higher density of electrons towards chlorine, chlorine becomes slightly negative. Okay? So the way we indicate that we have a slight negative is by the symbol called delta minus. Okay? This is like a D. Well, not really a D, but it is a D, okay, in Greek. And so this is delta. Delta means a small amount. Okay, and so this is delta negative chlorine because it pulls a little bit more electron towards itself, which means hydrogen must be delta positive then. And this is what we call a polar covalent bond. Polar for us means that something that has two poles. So for example, Earth also is polar, right? It has a north pole and a south pole. You can have a negative and a positive like a battery does, and that's what we're talking about here also. Okay, the polarity here is a positive and a negative polarity. So chlorine here is more negative, and then hydrogen here would be then positive. Okay, in there. It's not an ionic bond. It's still not a complete positive and a complete negative. If that happens, that would be classified as ionic. okay, completely. So it's not ions, okay? It's classified as a polar covalent bond then. Are we good? Okay. How do you decide if something is going to be polar or not? So for example, if you're trying to decide between carbon and hydrogen, how do you know? Nitrogen and hydrogen, is that going to be polar enough? Okay, and for that, you should have a table here in your textbooks, which gives you a little bit of a table. And when you subtract the two numbers, the numbers should come out to be 0.5 or more for it to be polar. And that table is on page 352, beautifully colored table there. And so it shows right here, fluorine is the most electronegative, okay? And then here, hydrogen and carbon, when you subtract the two numbers, it's 2.1 and 2.5, so that's 0.4 difference, okay, between the two electronegativity, which means it's very small, which means that bond is not polar. Okay, so it has to be 0.5 or higher. Do you have to memorize these numbers? No. Okay, you don't have to memorize them for me, but I want you to practice enough that you don't have to think that the carbon-hydrogen bond is polar. Do you see what I mean? Okay, so for example, if I give you a structure like this, and I ask you which one is the most polar bond, you're going to say it is?
Carbon.
And the bond.
Oh.
Which bond? Carbon-hydrogen, carbon-chlorine, carbon-iodine.
Carbon-chlorine.
Carbon-chlorine bond is the most polar. Okay, so that's what you will do. Good. And you know that as you go down the periodic table, the electronegativity decreases. So obviously the Cl is more electronegative than iodine is. Good. At this point, this is all you need to do regarding the polar bond. In the next chapter, we'll take it to the next level, but right now, that's what the main thing is. Okay, so when you look at a structure like, say, even something like water, do you have polar bonds here? Yes. Okay, oxygen is fairly electronegative, okay, because oxygen is right next to fluorine there. All right, so oxygen is 3.5 and hydrogen is 2.1. Okay, what I usually tell and recommend to students is at one time just look at the numbers and subtract a few of them, okay, and then just see, get an idea, okay, of what they look like, so that way hopefully it will stay in your memory, okay, but you have to do it at least once for it to stay in there. If you don't even do it once, it's not going to work, okay, so at least once you go through all the subtractions, okay, so for example, hydrogen is 2.1, iodine is 2.5. Do you think you'll have a polar bond? 2.1, 2.5? No. Okay, that's the subtraction I'm talking about. Carbon 2.5, iodine 2.5. Polar bond? No, that's 0. Okay, so which means that this is almost like, you know, having a bond between iodine and iodine. Okay, that's how much it is. So what I'm trying to say is if you do the subtraction at least once, hopefully it will stay in your memory. Okay, enough that you won't have to memorize any of those. And really, no, don't memorize any of that. It's not worth it. Okay, that is what we call polar bonds. Are we good so far? Yeah. Okay. So when you're indicating for this one, how do I write the arrows? Do we write it towards the oxygen or towards the hydrogen?
Towards the oxygen.
Towards the oxygen. Okay, so you have both arrows going towards the oxygen. Okay, and then oxygen is going to have the delta negative and hydrogen is going to have the delta positive, okay, on it. That's how you're going to show the polar bonds. Okay, I think we're almost towards the end of this chapter. Let me just see. Covalent bonds, multiple bonds with a single, double, triple bonds, electronegativity, dot formulas. And then we have resonance over here, exceptions to the octet rule, formal charges. The last two topics over here, they are bond length and bond order. Order just means the strength, okay, of a bond. So let me do this thing really quickly with you because I don't want to, again, memorize any of these numbers here. Okay, just give you a few bonds here. See if you can figure out what they would be like. Okay, for me right now, the bond length and the bond energy is not so important. Bond energy is the energy required to break a bond. Okay, and then the bond length is how big is this distance, okay, between the two atoms. So in some cases, it would be a lot closer than the others, okay? It'll be shorter than the others. Single bonds usually are going to be almost the same length, okay, in there. Yes?
Is the distance between them also called the ionic radii?
No. Ionic radii, that's how you're talking about atomic then. Because in ionic radii and atomic radii, that's a different thing. That you would do only for single atoms. This is bond length. Okay, so this is the bond length over here between the oxygen and hydrogen.
Okay.
Right. Okay. So here, let me write a few structures out. I'm going to ask you a couple of questions then. These are multiple bonds. Oh. So here we have carbon, three kinds of carbon bonds. Carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond, okay, over here. So for all of these three, we're going to do the two things, the bond length and the bond energy, okay? And I just want you to use your common sense, don't look in the book, all right? And see, tell me which bond do you think is the stronger one, the strongest one?
Triple bond?
The triple bond, okay, very good. So this is the strongest one. So, anybody else? Tell me why do you think it's the strongest one? Let me just, somebody said
Because
It's got a triple bond sharing electrons.
it's sharing more electrons, right, than single bond. Okay, yeah, so if you have more sharing of electrons going on, you have more overlaps going on. Okay, so right, very good. So that's the strongest bond, that must be then the weakest one. Are we good so far? Okay. Then the next thing is, of course, the bond length. Okay, so now which one is the longest? Which is the shortest? Pick whichever one, and I don't want anybody in the front to answer me. I want somebody from the back, okay, to answer. So which is the shortest? Let's go with the shortest. Okay. That's the shortest. Same reason, okay, because you're sharing 3 pairs of electrons, all right? And if you were thinking that, oh yeah, I knew that, I thought of that, well, why didn't you say something? Okay, don't do those kind of things. It doesn't work very well, okay? And, you know, at least in my class, you know that I like it if you talk, so please talk. You know. But anyhow, that's all that I need you to know as far as your bond length and your bond energy is concerned, okay? It's just the length and the short, and if you have to compare between single bonds and double bonds, that's all that I need right now, nothing else, okay, from there. But anyhow, the numbers are given for you over here in case you need it, but I don't think you need it. Okay. In your textbook, your end of the chapter problems are very good, okay? So please don't ignore them, all right? I can only give you so many molecules to write the Lewis structure of, so if you need more, you got a ton more. It's upside down, but it's still a lot.